So far we've collected data. We organized it in tables and charts and graphs, and then we measured our data. We looked at how it was clustered together with our measures of central tendency. We looked at how spread apart our data was, and that was our range and our standard deviation. And now we're going to look at a special type of distribution. Now, not all data, when you collect it, will have this type of histogram. However, if you do have what's called a normal distribution, it has some really nice properties. And that's what we're going to focus on for the remainder in 12.4, 12.5, normal distributions. So let's look at an example of a normal distribution. Let's just say that the mean height for a man is 5 feet 10 inches tall. And let's say that we have a random sample of 100 men. That would be represented by this first graph A. So let's just say then if we took the heights of these 100 men, that we got this first histogram or bar graph. Well, let's increase our sample size, and suppose that as we increase our sample size, and we'll look at graph B, we'll look at graph C. So as we increase our sample size, let's say that we have this really nice graph that seems really symmetrical. So it looks like D. If this is how our data is distributed in our histogram, then this is what we call a normal distribution. So in a normal distribution, you have your mean right in the middle, and you see that half the data is above, half the data is below, or it looks like this really nice curve. If you were to fold that graph along the mean, the two sides should match up. So this is a normal distribution. In a normal distribution, the mean, the median, and the mode are all going to be the same value. You may have also heard the term bell curve, or maybe the Gaussian distribution, or a Z distribution. So they all describe a normal distribution. If your instructor were to curve a class by the traditional curve method, then they would go with a normal distribution. What's nice about a normal distribution is we have what we call the 68, 95, 99.7 rule. What that says is that 68% of your data items will fall one standard deviation above the mean. So that would be represented, is that what I said? By this shaded portion of the graph. And then that -1 means one standard deviation below the mean. So 68% of all your data items will fall between plus and minus one standard deviation. And then 95% of your data items will fall between plus and minus two standard deviations. And this is about the mean. 99.7% of all your data items will be within 3 standard deviations, either above or below the mean. So if it's above the mean, then it's a positive number. If it's below the mean, it's a negative number. Let's go ahead and use this rule in example 1. So we have female adult heights in North America are approximately normally distributed. So we need to know that they're normally distributed so that we can use this graph. With a mean of 65 inches and a standard deviation of 3.5 inches. Find the height that is A, 3 standard deviations above the mean, B, 2 standard deviations below the mean, and C, 1.5 standard deviations above the mean. First of all, let's look at part A. We'll do this algebraically, so we'll write out an expression, and then we'll do it by using the graph. So 3 standard deviations above the mean says we're going to start with the mean of 65 and we're going to add to the mean because we're going above the mean. And in fact, we're going 3 standard deviations above the mean. So that's the mean plus 3 times the standard deviation of 3.5. That's 65 plus 10.5. and then 75.5 would be the answer, but remember we're looking at a height, so you do have to add on the units. In this case, they're inches. So the height that is 3 standard deviations above the mean is a height of 75.5 inches. Part B, we need to find the height that corresponds to 2 standard deviations below the mean. So be careful, because below the mean means that we're going to start with our mean of 65 and take away 2 standard deviations. So we're going to subtract 2 times 3.5, which would be 65 minus 7, and then that's 58 inches. Before we look at part C, I'd like to look at how we could use this graph. Remember in A, we wanted to go 3 standard deviations above the mean. So we want to find the height that corresponds to the graph of that positive 3, because that's 3 standard deviations above the mean. Well, where it's 0, that's the mean, and our mean was 65. If I were going to go 1 standard deviation, I would add 3.5 to get 68.5. If I was going to go to 2 standard deviations above, I'm going to add another 3.5 and I'll get 72. So 3 standard deviations, I would add another 3.5 to get 75.5. Part B, I was going 2 standard deviations below the mean. So I would start with the mean of 65 and I would subtract 3.5 to get 61.5. And then subtract 3.5 again, I would be at 58. The last one was part C. Part C, we want to look at 1.5 standard deviations above the mean. So in part C, we're going to start with the mean of 65. We're going to add 1.5, so I'm going to put 1.5, so it's easier to put in my calculator. 1.5 times the standard deviation of 3.5. So in my calculator, I get 70.25. Again, it's inches. Now using the graph for 1.5, or what if it said 1.24 standard deviations above the mean? That's a little bit harder. However, I can look at 1.5 standard deviations on that graph. It would be somewhere between 1 and 2, and the height of 70.25 falls within that range. So that's a reasonable answer. We'll look at another way that we can use this graph. So in our previous example, we were actually finding a data item. Our data item was a height. In example 2, we're actually going to be finding a percentage. Example 2 says male adult heights in North America are approximately normally distributed, so we need that, with a mean of 70 inches and a standard deviation of 4 inches. We're going to use the distribution of male adult heights to find the percentage of men in North America with heights, part A, between 62 inches and 78 inches, part B, between 70 inches and 78 inches, and then part C, above 74 inches. So think about what you're being asked to find. Previous example, we were asked to find the height. This example, we're asked to find the percentage, and that's really important. If you're asked to find a percentage, you're going to be using these percents on the graph, the 68, the 95, and the 99.7. In part A, it says between 62 inches and 78 inches. What I'm going to do is I'm just going to use this graph and I'm going to label it like I did a previous example. So remember 70 inches was our mean. So on my graph where the 0 is, I'm going to put a 70 there. And then the standard deviation is 4. So if I keep adding 4, I can get 1 standard deviation above the mean would be 74. And these are heights. And then 78. And then 82 would be the height that corresponds to 3 standard deviations above the mean. So 1 standard deviation below, I'm going to subtract 4 from 70 to get 66. And then I'm going to subtract 4 from 66 to get 62. And then subtract 4 again to get 58. Well, that's a sad looking 58. So I've labeled my graph, and I want to answer question part A. I want to find the percentage, so I'm going to look at the percents, the percentage of men who have a height between 62 inches and 78 inches. Let me go ahead and shade that. So 62 inches to 78 inches. I'm looking at the shaded green portion here. So what percent does that represent? Okay. So if you look at this, it corresponds to the 95%. Just by looking at the graph for A, I can see that 95, and have to put a percent on there, 95% of men have heights between 62 inches and 78 inches. Let's look at part B. Part B, we want to find the percentage of men who have heights between 70 inches and 78 inches. So 70 inches is the mean, and then 78 inches is 2 standard deviations above the mean. What is that percentage? So it would be this shaded region here in red. Now I have to get a little bit creative. I know that 95% of the data falls between the 62 and the 78. So between 70 and 78, that's half of the 95%. So I would take the 95% and I would divide it by 2 to get 47.5%. Let's look at C. In part C, we want to find the percent of men who have heights above 74 inches. All right, let's try black. So here we have 74 inches, and I want above. So it's going to be everything shaded above the 74. And that's even past the 3 standard deviations. Okay, so there's one way to look at this. And you may see it a different way, which is fine, as long as you get the correct percentage. The whole graph represents 100%. Okay? So if this whole graph is 100%, oops, there I go. And I take away 68%. So if I just take away the 68% from my graph, then what's left over is the above 74 and below 66. That's not the answer I want though. Okay, so I'm going to take away the 68. So what's left over is the above 74 and below 66. So above 74 would be represented by half of that, which would be 32% over 2, or 16%. That's not the only way that you can do this. But notice that to find the percentage, it's getting a little bit trickier by using the graph. We're going to look at a more efficient way to find percentages in a bit. But first, before we can do that, we're going to talk about what we call a z-score. So a z-score is just a number. It doesn't have units, it's just a number. And what that number tells us is it tells us the number of standard deviations above or below the mean. So the z-score can be negative, it could be positive, it could be 0, and it doesn't have to be a nice number. It could be 1.23. To compute the z-score, you're going to take your data item and you're going to subtract the mean. So you have to be careful since this is a subtraction, the order matters. It's always data item first minus mean. And then you divide by the standard deviation. For example, in example 3, the length of horse pregnancies from conception to birth is normally distributed, so that's important, with a mean of 336 days and a standard deviation of 3 days. We want to find a z-score for a horse pregnancy of, in part A, it would be 342 days. So notice that we have our mean, which is 336, and we have our standard deviation of 3. We're trying to find the z-score, so the only thing we need is the data item, which we have. Our data item is the 342 days. So to compute the z-score, and here we use z for z-score, for 342 days, so oftentimes when we're computing the z-score, we'll have the data item below as a subscript to indicate the z-score for the data item of 342 is equal to the data item of 342. We're going to subtract the mean of 336, and then we divide by the standard deviation. In this case, it's 3. 6 over 3 reduces to 2. What this is telling us is that the data item of 342 days is 2 standard deviations above the mean of 336. And it's above because it's a positive 2. So if the z-score is positive, your data item is above the mean. If the z-score is negative, your data item is below the mean. What about part B? We want to find the z-score, and I want blue. We were trying to find the z-score for the data item of 336. So it's our data item, 336, minus the mean. Well, in this case, the mean is 336 as well, over the standard deviation of 3. This is going to be 0 over 3, which is simply 0. We would never leave it as 0 over 3. We always simplify to an integer. Or in the case of z-scores, if you don't get a nice integer, then instead of leaving it as a fraction, like you wouldn't leave a z-score as 1/2. You would write it as the decimal 0.5. So the reason why this z-score is 0 is because our data item happens to be the mean. So it is 0 standard deviations away from the mean. Part C, we're trying to find the z-score for the data item of 333. So it's data item 333 minus the mean of 336 over a standard deviation of 3. That's negative 3 over 3, which would be a negative 1. So a horse pregnancy of 333 days is 1 standard deviation below the mean because it's negative. In example 4, we're going to compare the SAT and the ACT tests. So the SAT has a mean of 500 and a standard deviation of 100. The ACT has a mean score of 18 and a standard deviation of 6. So both tests measure the same kind of ability. The scores in this case are normally distributed. Suppose you score 550 on the SAT and 24 on the ACT. On which test did you have the better score? Well, unfortunately, it's not giving us how much the SAT test is worth, and it's not telling us how much the ACT test is worth. The only information we have from those two tests is their mean and their standard deviation. But remember what the standard deviation says. It says how far away you are from the mean or the average. So the higher your z-score, which tells you how many standard deviations you are away from the mean, the higher the z-score, the better you scored on the test. So all we have to do in this case is just compute the z-scores for the SAT and the z-score for the ACT, and the higher z-score tells you that you performed better on that test. Let's look at SAT first. We're trying to compute a z-score. We scored 550 for 550. So that's our data item, 550. We're going to subtract the mean, which was 500, and we divide by the standard deviation of 100. This would be 50 over 100. This is going to be the decimal 0.5. Now let's compare this to the ACT. Well, the z-score is positive, which means that you scored above the average score, which is good. But on the ACT, I think that's going to be higher. We're looking at a z-score for 24. That's what we scored. So it's our data item 24 minus the mean. In this case, our mean, where's our mean? 18. Our mean was 18, and the standard deviation was 6, which gives us 6 over 6, a z-score of 1. So since this is a higher z-score, that means that we scored better on the ACT. And we could figure out which one we scored better on without even knowing how much the ACT or the SAT tests are worth. We'll look at another example. We'll look at those IQ tests. I don't know if you've ever taken an IQ test. Quite frankly, I don't believe in the IQ tests. To me, it just tests on pattern recognition and grammar, which I don't feel is a sign of intelligence. However, in example 5, intelligent quotients, IQs on what we call the Stanford-Binet intelligent test are normally distributed with a mean of 100 and a standard deviation of 16. So we want to find the IQ corresponding to a z-score of negative 2.25. This is a little bit different. In the previous example, we were asked to find the z-score, but here we're actually given the z-score in part A of negative 2.25. We're given the mean, and we're given our standard deviation. So when we're trying to find the IQ, that's our data item that we're trying to find because we have all the other pieces. And we're going to be looking at the z-score. So I'm going to just write z for z-score equal to data item. We subtract the mean, and instead of writing standard deviation, I'm just going to write SD for standard deviation. So we're going to be using that formula since we have all the pieces to that formula except the data item. So let's think about what this is. We're going to take our z-score of negative 2.25. It's going to be equal to our data item. In this case, our data item is our IQ score that we're trying to find, minus the mean is 100, and the standard deviation is 16. So we have this equation. We're trying to solve for the IQ score. So algebraically, what we would do is we would first multiply both sides by 16 to get rid of the fraction. So if I multiply by 16 on both sides, the 16 cancels on the right. On the left-hand side, I'm going to leave it this way. I'm going to leave it as 16 times negative 2.25 equal to the IQ score I'm trying to find minus 100. So to get the IQ score by itself, I would add 100 to both sides. If I were to add 100 to both sides, the hundreds on the right-hand side would cancel. I would end up with 100 plus 16 times negative 2.25 equal to my IQ score. So now I just have to put this in the calculator. And then when I do that, I will get 64. So an IQ score of 64 is 2.25 standard deviations below the mean because this z-score is negative. That answer makes sense. But this is kind of a pain to solve for the data item. So instead of using the z-score formula that we have, if we simply take the original formula and we solve for the data item, we have what's in the box below. So whenever you're trying to find the data item, it's going to be the mean, which in our case, our mean was 100. So let's look at this last piece here. We have our mean plus, and in this case, I had my standard deviation, and the negative 2.25, that's my z-score, and then the IQ is my data item. So if I solve the z-score formula for the data item, then it ends up that the data item is equal to mean plus z-score times standard deviation. Since this is multiplication, the order didn't matter. Standard deviation times the z-score times standard deviation, either way. So again, if you're trying to find the data item, it's better to use this formula in the box rather than using the original z-score formula. So let's try that formula with part B. We want to find the IQ score, which is our data item. That corresponds to a z-score of 1.75. So that's going to be our mean plus the z-score of 1.75 times the standard deviation of 16. And then you would just plug that into a calculator. And when I do that, I get 128. So that would be the IQ score that corresponds to a z-score of 1.75. All right, next thing I want to talk about is percentiles, and I'm sure you've heard that term percentile. So when we talk about a percentile, if you have n% of data items in a distribution that are less than a particular data item, then the data item is in the nth percentile. So that's just a lot of words. What does that mean? Okay, so first of all, when we say less than, that means below. So the data item's below a particular data item. So it's the percent below a particular data item. That's our percentile. For example, a student scored in the 75th percentile on the SAT. What does that mean? That means that 75% of all scores are below this student's score. Okay, so the percentile gives you the percentage below. Okay, and it's really important that we talk about the percentage below. This is going to become important in the last section that we're going to cover, which is 12.5. The last thing we're going to talk about in this section is what we call the margin of error. So remember that we collect this data, but we're only sampling our population. We're actually not collecting data from every person in our population, so there is going to be some error there. And that comes with this margin of error formula. So if you have a random sample of size n, so n is just the number of the number of people you sampled, then there is a 95% probability that a statistic lies within 1 over the square root of n of the true population statistic, where plus or minus 1 over the square root of n, that's what we call the margin of error. Again, this is all a bunch of words until we actually apply this margin of error. Example 7, a Harris poll of 2,513 US adults ages 18 and older found that 36% read 10 or more books per year. So we have this statistic, we have this random sample, we have these results. We want to find the margin of error for this survey, and then we're going to round to the nearest tenth of a percent. So tenth of a percent, the tenth, that would be 1 decimal place. So the margin of error is 1 over the square root of n. But then we always have this plus or minus in front of it, and that's actually important. We need to have that there. Our n is the size of our sample. In this case, it's 2,513. Our margin of error is going to be plus or minus 1 over the square root of 2513. So you're not going to put the plus or minus in your calculator. What you're going to put in your calculator is 1 divided by the square root of 2513. When we do that, it's going to be approximately equal to, I'll write down what's on my calculator. With the plus or minus, you've got to have that plus or minus there because that is the margin of error with the plus and minus. I have 0.01995. I'll take it out to 1, 2, 3, 4, 5, 5 decimal places. And then it says to round to the nearest tenth of a percent. That would be 1 decimal place. Now, the problem is that when we write the margin of error, we always write our margin of error as a percent because this is the tenth of a percent. But this answer is not a percent, it's still a decimal. So I'm going to have to move my decimal over 2 places to get 1.995. That would be the percent. So just be careful about what you're asked to find. If you're supposed to round the margin of error to the tenth of a percent, you have to first write it as a percent and then round it. Now this says to 1 decimal place. So our margin of error is actually going to round to 2.0%. And this is my margin of error. That would be part A. So we're going to write a confidence statement about the results of this survey. Now this confidence statement comes about with this 95% probability. So we're going to use this idea that we can be 95% confident about our results. And it's only 95% because there's always error. We're going to start out the same. We can be 95% confident. So this is a confident statement, if I could spell confident. So we can be 95% confident that between, and this is where we're going to look at our data. So our result was that 36% of the people that we sampled said they read 10 or more books per year. But we had this error of plus or minus 2%. So we're going to add the 2% and we're going to subtract the 2% from our result of 36%. So when we add the 2%, we're at 38%. And when we subtract the margin of error, the 2% from 36, we're at 34. So that means we can be 95% confident that between 34%, so that would be if I subtract my margin of error from my result, and 38%. So I'm going to add my margin of error to my result of, and then just reword the problem, of US adults age 18 or older, read or read 10 or more books per year. So when my lab asks you for a confidence statement, it's always we can be 95% confident that between, and then you would just add and subtract your margin of error from your percent result. Okay, part C. Why might some people not respond honestly to the survey? So we have error whenever we look at our data because, for one, we're not sampling the whole population, we're just sampling a portion of our population. And another thing that could happen, especially with surveys, is people might not tell the truth. And that would skew the results as well. So one of the reasons in this particular survey why somebody might not respond honestly is maybe they don't want to look stupid. So maybe they don't want to admit that they don't read a lot. Amongst other reasons. The point being is that whenever you are collecting your data, you got to take it with a grain of salt. There could be errors in people responding to whatever your research is. There could be errors in your own measurements of whatever it is, like, measuring people's heights. Maybe there's an error as you measure. And there could be the idea that maybe your sample size wasn't representative of your population, or maybe it was just too small to get any honest results. That's it for this section. And in the next section, the last section that we're going to cover in this course, 12.5, we're going to look at a better way to compute percentages rather than looking at the percentage chart that's 68, 95, 99.7%. So that's it.